So let's put on the board a probability distribution that's both very common and simple enough to work with. We saw what we call the normal distribution, the bell curve yesterday, but we also saw that the probability density function was kind of a beast for that one. So the experiment here is waiting for something to happen. And X, so our random variable, is going to be the time it takes for that thing to happen. So, you're going fishing and you want to catch a fish, then you're looking at how long it takes to catch a fish. Or you have a light bulb and you might expect that if you buy 2 light bulbs of the same brand, they're going to burn out at the same time. That really doesn't happen in practice. Sometimes light bulbs last years longer, and there's no reason why that anybody can see. It just happens. So we're going to look at the specific situation where this random variable is what we call memoryless. And by memoryless, we mean that the amount of time we've spent waiting doesn't affect the probability that the thing happens. Like, look at a lottery. Like when you see, such and such $1 billion lottery, nobody's won it. I mean, nobody has the ability to look at the numbers people have already picked and base their decisions on that. It's just the chance that somebody wins the lottery today is exactly the same as the chance that somebody wins the lottery tomorrow. We're going back to the fishing. I mean, the fish are not saying to themselves, well, he's been waiting a while now, we'd better toss him a bone. The fish bite when the fish bite, and it doesn't matter how long you've been waiting. So in a situation like this, the probability distribution, now depending on how you want to write it, to me, the sensible thing is to say, well, if we're waiting for something to happen, time has to be positive, so we're stuck on the interval from 0 to infinity. And then the probability distribution is a constant times the exponential to that same constant with a negative sign in front of it times x. What you'll sometimes see, it seems a little goofy to me, but people will want probability distributions to be defined on the entire interval, on the entire real number line. And when you're in a situation like this, where it just isn't defined on the real number line, they'll use piecewise defined functions. They'll say, Well, it's defined on the real number line, but the probability is 0 a bunch of the time. So we can't actually have negative values. To me, this is a technicality that's not adding a whole lot of value. So I'll just take a look at this. And this is a probability distribution. So I guess I sort of take it for granted, but I should say it explicitly that C has to be positive here. So this is a probability distribution. And I mean, what did we need for that? Well, we needed it to be positive. And here we've got a product, and C is positive, and an exponential function is always positive. So a positive times a positive is a positive. Check there. We need it to be continuous, or at least we need it to not be too badly discontinuous. If we're thinking about the probability distribution like that, there's no problem. The exponential function is continuous. If we want to think of it as a piecewise defined function, there's a jump, but that turns out to be okay. One jump does not make it badly discontinuous. So there's a break at 0, but that doesn't hurt anything. And then the more substantial requirement is that this has to be equal to 1. Again, repeating what I said yesterday, this is representing the fact that we're assuming something happens. I mean, we're assuming that, I say assuming, it's not so much an assumption as a theory of probability, that if something can happen and you wait long enough, that thing will happen. I mean, it's the old monkeys with the typewriter thing. So we need this for this to be a probability distribution. And let's see. The limit as n goes to infinity, the integral from 0 to n. This, of course, is an improper integral. C e to the negative cx equals, we could use U substitution here if necessary. When I say if necessary, I mean that maybe we can do this in our head, but if we can't, it's okay. The U substitution works out almost perfectly. The only thing is that we're missing a negative sign. We're missing that negative sign inside the integral, but we can put it in. This is negative e to the negative cx evaluated from 0 to n. Negative e to the negative nx plus e to the negative c times 0. And this plus sign comes from the fact that when you're using the fundamental theorem, you're doing subtraction. We subtract a negative, it turns into addition. And now it sort of depends on what you know of little. Well, let's go to Desmos and let's check our work. So this is supposed to be 1. E to the power of 0 equals 1. So what I sure hope is happening here is that is approaching 0 as we go to infinity. That was a typo, by the way. We're plugging n in for x, so we've still got that c there. Let's just quickly take a look at this graph. Little worried about that negative sign in front of the e. If it weren't there, I'd be happy, but negative e to the negative, well, we don't know what c is, but c could be any number. Let's just put, oh, nope, works perfectly. I don't know what I was envisioning, but as n is going to infinity, this is indeed going to 0. I didn't share that screen, so you're watching the recording, you didn't see anything, but I just verified this. So this integral is equal to 1, and this is a probability distribution. Now, when we have a probability distribution, well, first of all, we can ask questions. I mean, let's say we're fishing and we want to know the probability of catching a fish in under 2 hours. So we're looking at the interval from 0 to 2, and we're looking at the integral from 0 to 2 of, let's see, we need a c here. This c controls how likely something is to happen. Let's say in this particular situation, it's 3, e to the negative 3x. So the integral from 0 to 2 of 3 e to the negative 3x dx equals, again, we can hit this with u substitution, but we wind up with negative e to the negative 3x evaluated from 0 to 2. Negative e to the negative 6 plus e to the 0. And this is going to be, I believe, quite close to 1. I never did get that calculator working. It would be more accurate to say that I forgot that was a thing I needed to do. But if we go to Wolfram alpha, negative e to the negative 6. Type it here, or to search the internet. Negative e to the negative 6 plus e to the 0 is 1, and about 0.998. So if this is accurate, a very high probability that we catch a fish without waiting too long. And this sort of raises a question. I mean, we look at this and we see, well, we probably don't have to wait 2 hours. On average, how long do we have to wait? I mean, again, this is a slightly informal question, because the answer to it is going to be a number, and then, well, the probability that we have to wait exactly that amount of time is actually 0. But, you know, if we perform this experiment 10 billion times and averaged the results together, what would that average be? I mean, we can think of it informally like that. And we've got a probability distribution on some interval. These endpoints can be open and closed. It doesn't matter because the probability of getting one of those endpoints is 0, so it doesn't matter if we include them or not. So the expected value is the integral over the whole thing of x times e of x dx. And when I was introducing integration by parts, I said, well, this is a pretty specialized technique, but it shows up in some pretty significant applications. And I mean, what we have here, obviously it depends on how complicated P of X is, but it looks like a classic integration by parts. And if we go back to this example and we ask the question, so on average, how long do we have to wait? The integral from 0 to infinity of, was that 3 x times 3 times e to the negative 3x. That 3 can pull out. This is exactly an integration by parts problem. You can tell me if it gets too cold in here. I struggle with the heat. And what makes this an integration by parts problem is that we've got a product, and one of the terms becomes nicer when we differentiate it, and the other term is easy to integrate, or let's say relatively straightforward to integrate. Let's do this. I would like to brush aside for the moment the improper integral side of things, because that can become sort of notationally messy. So what I'll do is I'll just find the antiderivative using integration by parts. And once I have the antiderivative, I can mess around with limits as stuff goes to infinity. And if I don't put that 3 in front, I'm definitely going to forget it. So let me put that there too. Okay, so what would a good choice of U be? So I hear negative 3x. We have, I would suggest that that's probably not going to work great. And the reason, I mean, obviously, I always appreciate when people answer my questions instead of just sitting there. The reason I suspect it's not going to be great, though, is that we'd really like something that becomes nicer when we differentiate it. We're going to go from U to du, and negative 3x, going from U to du isn't very appealing. It's not making that problem any simpler. The sort of guideline, and like all guidelines, I'm sure you can find exceptions to it, is this acronym, whatever you'd call it, mnemonic, memory aid, like it. There are no logarithms, there are no inverse trig functions, but x is an algebraic function. Algebraic functions are like polynomials and square roots and stuff. And you see that if we let u be x, we get real simplification here. Du ends up being 1. Did not bizarre typo. If we let du be e to the negative 3x dx, then v is the integral of that, which is what? Yeah, I've been doing these in my head, and maybe I shouldn't be. This is a little u substitution. We've got composition. We've got that stuck inside the exponent. If we let u be that, then du does not equal that. I'm imagining a future where I put a negative 1/3 in, and it's sort of bleeding into my current work. So we don't have a negative 3, but we can put a negative 3 in there as long as we balance it out. Negative 1/3. And now this and this. And that turned into du. And this e to the negative 3x is e to the u. And the integral of e to the u is e to the u. The exponential is its own integral. Negative 1/3 e to the negative 3x. Plus a constant of integration, which we are not going to bother with because we're taking a definite integral at the end of the day. If you're wondering what I'm doing when I'm talking about taking integrals in my head, I'm certainly not doing this. I'm saying to myself, well, the derivative of e to the negative 3x is negative 3 e to the negative 3x. So I'd better throw in a negative 1/3 to get rid of that negative 3. And if you're not comfortable with that, this is obviously a perfectly fine way of approaching the problem. Then we've got this 3 out front. Let's not forget that. We've got u times v. Negative 1/3 e to the negative 3x times x. Don't want to forget that u. Minus the integral of v du. Well, du is 1. And let's see, this minus and that minus together make addition. There's no real great place to go here. I guess just go to another frame. 3 other frames all full up. 3, then negative 1/3 x e to the negative 3x. Plus and you can again hit this with u substitution. U equals negative 3x. Let's see, but it's e to the negative, it's 1/9 e to the negative 3x. And again, you can do this with u substitution. I'm just thinking this through. Well, if we take the derivative of this, we'll get a negative 3. We want to have a positive 1/3. Negative 3 and negative 1/9 together give you positive 1/3. So we're plussing a negative that will turn into subtraction. 1/9 e to the negative 3x. And that 3 distributes. If you find these very lengthy integrals a little demoralizing, I can only say that I do too, but you've just got to take it one step at a time. And now that we have the antiderivative, what we actually want is we're taking this thing. We ended up bringing that 3 right back in after taking it out, but we're going from 0 to infinity. So the limit as n goes to infinity, negative x e to the negative 3x minus 1/3 e the negative 3x from 0 to n. And now the real question is whether we're going to wind up with the correct thing, and just eyeballing this, I believe that we are. So it's actually really bringing a lot of stuff together. So we've got negative n e to the negative 3x. Or rather, we've got negative n e to the 3n. We've got negative 1/3 e to the negative 3n. Then we subtract. When we subtract, both these additions are going to turn into addition. What did I say? Both these subtractions are going to turn into addition. So we're going to have plus, and now we're plugging in 0. This looks messy. It's exactly what it needs to be. A lot of these terms, or rather 2 of these terms, end up being okay. This 0 times anything is 0. Nothing to worry about there. I, for some reason, was unsure about this a little earlier, even though I know perfectly well that e to a negative number does go to 0 as we go to infinity. I was a little confused by the negative in front, but the negative in front doesn't stop it from going to 0. So this is going to 0. Negative n e to the negative 3n is actually indeterminate. It's indeterminate, the form infinity over infinity. The numerator is going to infinity, the denominator is going to infinity. But you hit this with L'Hopital's rule. you, writing this a little informally, of course, wind up with -1/infinity, and that's 0. Whereas here, e to the 0 equals 1. The only thing that makes it out of that is a 1/3 curve. So you might, sometimes you'll have to wait longer. Sometimes you might get something right away. But the expected value, the amount of time you expect to have to wait before you get a fish, is 1/3 of an hour. And that 1/3, you look at the that probability distribution, you see a 3 is showing up there as well. That's no coincidence. The expected value, we write it with that Greek letter. You might have seen that before if you've ever taken some kind of probability. The expected value is 1/c. And now the next one piece of material more. We have to wrap up pretty soon because I'm on a job search committee and we are giving an interview at 11, but at 9. We have about 15 more minutes, so let's just mention the variance and the standard deviation. Let's look at two probability distributions. Let's say from 0 to 1. And now I'll just say there are probability distributions. We won't mess around trying to make the areas work. But this could be a probability distribution. The area under the curve there is 1/2. The area under the curve there is 1/2. So the integral is 1. And if the area under that spike is 1, that is also a probability distribution. They are both positive, or at least non-negative. They're both continuous. Their integrals are 1. No problem. Both of these have the same expected value. Because of the symmetry of the graph, high values are exactly as likely as low values. If you calculated these, they would both have expected values of 1/2. But these are very different probability distributions, and that 1/2 is only doing a good job of describing the data in one of these cases. So even though our expected value is 1/2, over here we can never get values that are close to 1/2. The integral of this, for example, the probability of being in that region is 0. So the only values we can get are values that are really close to 1 and values that are really close to zero. We have that expected value, but it's not representing the actual values we can get. Whereas over here, the only values we can get are in that little interval around 1/2. The expected value is doing a good job of summarizing the data. And in mathematical terms, we would say that the value on the left has high variance, and the distribution on the right has low variance. And that word, variance, gives you a clue about what this means. The expected value is about 1/2. Variance is telling you how much we vary from that. So here, we vary from the expected value a lot. In fact, we cannot be close to it. Here, we don't vary from the expected value a lot. We have to be close to it. And this is variance. And variance, it's sometimes called var. It's sometimes written sigma squared for reasons that will appear. Whatever you call it, it's x minus the expected value squared times the probability distribution. So we're not actually going to do this. We wouldn't have time, but when we did integration by parts, we looked at examples where you have to use integration by parts twice, or even potentially more than twice. And this is an example of how that shows up in real application. If you use integration by parts, that's our u, that's our dv. I know this is probably hard to see, but we wind up with this. And then when you hit that, you have to use integration by parts a second time to take it. So if nothing else, it's a nice demonstration that some of these more complicated examples we do not do to bedevil students. We do because they do show up in applications we want. The variance is, well, you see I gave this notation. The variance is something squared. The variance is not the best way of talking about how spread out data is. Among other things, this square means that your units are going to be weird if you use variance. Like if your variable is time in hours, your variance is going to be in hours squared. And what's an hour squared? That's a kind of weird thing to have. So what you'll see a lot more often is the standard deviation. And the standard deviation is written, this Greek letter sigma, I believe, and well, if the variance is written as sigma squared, you can probably guess how sigma is defined. The standard deviation is the square root of the variance. And that gets your unit back to something that makes sense. If your data is in hours, the standard deviation will be in hours. All right, so tomorrow, I'll be in the classroom. There's no new material. There is that old test I posted. If anyone has questions that they want answered before the Thursday test, come in. Otherwise, you can sleep in, I guess. I'll see you either tomorrow or Thursday.